Okay, today I'm going to go through part 2 of this exam run-through. This was a special request. Someone's noticed that I hadn't done the June 2023 run-through. Actually, I'd had my solutions were ready, and probably I ran out of time last year. So these have been ready for a year. So thank you to the person who noticed that this Unit 5 Pearson Edexcel Physics Unit 5 was missing. And it covers thermodynamics, radioactivity, nuclear physics, radiation. It's like atomic and nuclear physics together. Oscillations, so like simple harmonic motion, and space physics, cosmology. Okay, so in part 1 I went through the multiple choice questions, and I also went through the first of the structured questions. And today I'm going to go through the topics which you would need to revise thermodynamics with. Okay, so here you have an airbag, which is a safety feature used in cars, as you all know. Nitrogen gas is released into an airbag. The airbag inflates to a volume provided to 3 significant figures in meters cubed. The pressure of the gas is inflated in the airbag. In the inflated airbag is given. So you know the pressure and the volume. Again, 3 significant figures are being used. Now, one person wrote to me asking me if you have a combination of data provided to sum to 3 significant figures, sum to 2 significant figures, what should your final answer be? Well, if that's the case, then you can choose, but normally you should err on the side of caution. Now, the person who wrote that request didn't comment in the section under the video, but had written an email to me, which my email is visible somewhere on the homepage. But really, the best place to do that would be in the comments section underneath the video. You will get your response quicker. Also, if you're a member, your questions will be prioritized. Membership is now available because the channel has grown to over 1,300 subscribers. So the question wants you to show the number of molecules of nitrogen gas released into the airbag is this value. And you can see they only want it to 1 significant figures. Now, the number of molecules is N in the equation, which is provided on your equation sheet. Pressure times volume is number of molecules times the constant times the temperature in Kelvin. They then give you the temperature in Celsius just to see that you can change the equation in the number into Kelvin. So the only thing you don't know is N. It's such a simple question. So you'd probably get 1 mark for doing the conversion to Kelvin, and they want to see that you can do that. So it's just a warm-up question for the thermodynamics section of the course. K is provided on a data sheet, and all the other numbers are given to 3 significant figures. So you should quote your answer to 3 significant figures, and then say, well, look, this is equal to approximately 2 times 10 to the 24, which is what the question wanted you to show. Remember, if you have a show that question, it means they want you to prove it mathematically, okay? All right, so we have shown that N is approximately 2 times 10 to the 24, which, if you remember Avogadro's number, is about 10 times Avogadro's number. Is it? No, about 3 or 4 times Avogadro's number. The next question, next part of this question goes into nitrogen gas escapes from the small hole in the airbag. The pressure decreases, so you have a new pressure, again to 3 significant figures. Calculate the number of nitrogen molecules that escape. In other words, there's going to be a change in the nitrogen number from original N1 to N2. the volume remains constant. Yeah? And I put here that the temperature remains constant. Okay, so we're assuming the temperature does not change. So if pressure doesn't change, if the volume doesn't change, K is obviously a constant, and temperature doesn't change, yeah, then the pressure must be directly proportional to the number of molecules. So in other words, the pressure is due to the number of molecules. If you remember, even in GCSE, you know the kinetic theory of gases, which is the collisions, the rate of collisions of the particles is what determines the pressure in a gas. So you can make a simple formula, a bit like the pressure law, but this time ratio of P's will be equal to the ratio of N's. So since we know both the pressures here, all it is a matter of ratios. You multiply the ratio by the original number, and because the pressure has gone down, we can work out how much the number has gone down. So it's gone down to 5.93 times 10 to the 23. And the original pressure we had from part before to 3 significant figures was here. Take away the second value we just worked out for N2 on this line, and you can work out the difference in the number of molecules as being 1.54 times 10 to the 24. Yeah, always make sure you use the accurate value. Yeah, at least 3 significant figures from part A. Don't use the rounded up values, which is a common mistake students make. Okay, so that's question 12 done. Question 13 I'm not going to do now. I'm going to do a different section for the questions which cover a different topic. So I'm going to concentrate on thermodynamics questions in part 2. So here's the mark scheme. Yeah, you can stop the video and take a look to see where they're given the marks for. Question 13 I'm going to come back to. And look at question 14 because it's a related topic to what we just went through. Ice cubes can be made in an ice cube tray for the fridge. One type of ice cube tray is shown. Each compartment in the one shown, has dimensions which are pretty much a cuboid. You've got the dimensions in centimeters. So don't forget SI units will be needed at some stage. So show that the mass of water needed is about 0.02 kilograms. So once again, show that is about. So again, they want you just to show it to one significant figure, but your calculations will have to be accurate. Density of water is given in kilograms per meter cubed. So you've got to make sure you have consistent units. Volume is very simply put as length times width times height. 10 to the minus 2 because we're changing centimeters for each one into meters. So we get a volume of 2.19 times 10 to the minus 5 meters cubed. Multiply that volume by the density and you'll get the mass of the water, which comes out to 2.19 times 10 to the minus 2, or 219 grams, which is approximately 0.02 kilograms to one significant figure. Okay? Probably we shouldn't have put our answer here to 3 significant figures, but 2. We should have done it to 2 because you can see the data provided is mostly 2 significant figures. Okay? So this is question 14. So here they're accepting a minimum of 2 significant figures as your calculated value, and then you say this is approximately 0.02 kilograms. 14 has another part, so we'll come to that. Looks like it's specific heat capacity. and latent heat and power. So these are very common questions in Unit 5, okay? So you can go back to this part and stop the video if you want to check the mark scheme directly, which is always a good thing to do. Check your mark schemes, see what they give marks for, and see what doesn't give you marks. So all 6 components in the ice cube tray are filled with water to the depth of 3.5 centimeters, and then the ice cube is placed in a tray, and obviously the freezer cools down the water and makes it ice. So the total mass will be 6 lots of M from part A. So we know to 3 significant figures how much water we're talking about in kilograms. The initial temperature of the water is from the tap, no doubt, 22.5 degrees centigrade. So that's the initial temperature. And it takes 12 minutes for the water to become 0 degrees centigrade. So that 12 minutes is 720 seconds. Yeah. So the specific heat capacity equation is given to you in the data sheet. So it first brings the temperature down to 0 degrees centigrade, and then there is a change of state. And as you know, the change of state, there is no temperature change. All the energy that the freezer is taking out of the water goes into creating the bonds that freezes the ice together. And it's L times delta M. So the second phase will be to do with making ice from water. The manufacturer of the freezer states that the freezer can generate or transfer energy at a rate of 110 watts, okay? And of course then we have this power, which is a revision of Unit 1. For those of you doing Edexcel in linear, your exam will have a lot of linkages from Units 1 and 2 in your Year 13 exams. So these are excellent practice papers for people doing linear exams, because there are more modular than there are linear. So evaluate whether energy is transferred from the water at this rate. So it's another show that. Evaluate instead of show that the rate is rate of transfer of energy is about 110 watts. So they want you to get what you think the power is. Okay, so obviously there is a total amount of energy transferred. We've got to use a specific heat capacity given here, and we've got to use the specific latent heat of fusion used there. So we're using these 2 equations to see how much energy has been removed from the internal energy of the water that we put in the ice cube maker overall. So the energy absorbed, the total energy transferred from the water, will be due to the temperature change, so the specific heat capacity equation, plus the bonds made to freeze the water. So the first part of the equation is 6 lots of ice cubes, which we worked out in part A, that's the mass, 4,180, the specific heat capacity, which is provided here, and the temperature change from 22.5 degrees to 0. So that's how much energy got to get it to freezing point, and then at the freezing point, all the energy then from the freezer goes into the mass and converting it from liquid to water. So this time you have to put this value into ml. So that's the L value. Okay, so those 2 brackets need to be added up. Once you do that, you'll see the total energy provided or transferred out of the water is a fixed value according to the 2 equations. So we know how much energy was transferred from the warm water by the freezer. And if you know it took 720 seconds, and you know that power is energy divided by time, then you just you divide the value you just calculated by 720 seconds, and you'll see that it's removing the heat at a rate of 78.5 watts, yeah, or 78.5 joules per second, which is less than the 110 watts that the manufacturer claims. So the energy is transferred to a tray at less than the value that they want us to evaluate. Okay, so you're going back once again to the original question. Okay, that's question 14 done. We've done 12, 14. I want to do one more question, which I noticed was on this similar topic. There it is. It's to do with temperature. So again, thermodynamics. This time it's a 6 marker, looks like. And we're going to use the mark scheme. The wax is heated under temperature until the temperature of the melting point of the wax, until the temperature is above the melting point of the wax. And the hot wax is then poured into a bowl and allowed to cool. So first you heat it, so when you heat it, you get to the top of the graph, and then you let it cool. Okay, so the graph shows how the temperature of the wax varies as it cools. So this is a cooling curve. You can see it's cooling. It's a curve, yes. It's not a straight line. And then over here you've got a change in state, and then it starts to cool again. So you've got start with liquid, and here you've got solid, and here you've got the transition between liquid and solid. And why did I put change in potential energy? Because a change in state is a change in the bonds, and that's a kind of potential energy store, okay, that can be released. So that's where we got the energy equals mass times the latent heat. And latent means hidden, so it's a potential energy that is involved. Whereas when you are losing temperature, you have the kinetic energy of the particles decreasing mainly. Okay, so temperature is related more to kinetic energy and bonds to potential energy. Okay, so it says describe how the internal energy of the wax changes as it cools. Okay, so we're looking at changes. The sum of the potential and kinetic energies is the internal energy. Okay, you should refer to the energy of the wax molecules as the liquid cools and becomes a solid, and then the solid cools. The 3 stages which I've already talked about. So the internal energy times x and y have been included to help you refer to the graph. So time x is the beginning of the change of state, and time y is when it's all solidified. Okay, so x is the beginning of solidification and y is the end of the solidification. So internal energy is the sum of potential and kinetic energy of molecules, okay, obviously of wax. So that's the first thing to show that you know what internal energy means. You'll probably get a mark just for saying something like that. The internal energy of the wax decreases over time as it cools and changes state. Okay, so yes, so where is it losing its internal energy to? Yeah, it's something for you to think about. Obviously, it's going to be to the surroundings. As the temperature decreases, and the negative gradients of the graph show that the temperature is decreasing, the molecular kinetic energy decreases. Yes? So, between x and y on the graph, the wax is solidifying. Yeah? And only the potential energy between the molecules decreases between x and y. Okay? So you have to put it in these phases. Before x, yeah? So this is before x. This is between x and y. and then we're going to go to the final phase. Between X and Y, therefore, the temperature remains constant. So it's a good point to make to show the examiner you know that temperature doesn't change during a change of state. There is no longer change in the mean molecular kinetic energy. It's just due to the bonding that's taking place, okay, between the molecules. At Y then, all the wax has solidified. So have we answered the question? Let's go back to the question C. Describe how the internal energy changes, yeah, as the wax cools. What we have, you should refer to the energy of the wax molecules as the liquid cools, which we did before X, and becomes solid, and the solid wax cools, okay? So after, at Y, all the wax has solidified, I should add, and the kinetic energy starts to decrease again. And that's the bit I hadn't put, which I just noticed, because you can see it's on a downward slope again. Yeah, so the kinetic energy is decreasing. So I hadn't verbalized this stage, so I could have lost the mark. And that's the 6 marker. And 6 markers, and this is the last question on thermodynamics that I noticed in this paper. The 6 markers, you get 4 marks for the kind of content that I've put in, and the 2 marks they give you is if your answer shows a coherent and logical structure with linkages and fully sustained lines of reasoning throughout your answer. So they want to look at the way you're writing and if there's any confusion in the way you're explaining things. Okay, so I'd have got the 2 marks, and if your answer is partially structured, you'll get 1 mark. So they only give you 4 marks for the content and 2 marks for the way you're reasoning your answer. Okay, all right, so I think my answer will get the 6 marks, and I hope you found this video useful, and then I'll make a follow-up video and I'll try and put the questions which are of a similar topic in the same video. Okay, so if you're doing modular or linear, this is a very useful revision of the Year 13 content for the thermodynamics topics. Okay, thanks for watching. Don't forget to like it, share it with any classmates, and subscribe so you know when the next video is uploaded. And I've had some requests for some linear papers as well, and I will try and build them in. Try and become members, because that will give me more incentive, because basically it's a small charge for becoming a member, and that will give you priority requesting. Okay, bye for now.